Well, so today we are going to discuss the property estimation of real gases and other substances, of course, but they will be primarily confined to real gases. Now, to a quick recap before we go for the property estimation part. If you remember, in the last class, or rather few classes before this, what did we do? We used the Maxwell's equation in order to express certain non-measurable properties in terms of measurable ones. What were the different non-measurable properties? We tried to express the change in entropy with change in measurable properties, primarily T and P or T and V. They are given by the first two equations here. Then from there, what we tried to do, we tried to find out we tried to express the change in enthalpy and the change in internal energy again in terms of the PVT behavior of the gases and also the CPCV, the specific heat property data. And after that, we also did a few other things. For example, we tried to express Cp minus Cv in this term. We tried to express Cp by Cv and so on and so forth. We had tried to derive several such properties in terms of the PVT behavior of gases. And then we found that unless we know the PVT behavior, we will not be in a position to exploit these equations further. So therefore, we had discussed the PVT behavior of gases. We had discussed both the mathematical equations as well as the graphical representations, and of course, I had mentioned that there are some tables as well which can be used for this purpose. Now, once we are aware of the PVT behavior of gases, now we can use whatever information we have at hand in order to find out, or rather in order to express your enthalpy, entropy, internal energy, etc., even Cp, Cv, etc., in terms of the PVT behavior of the gases. Now, I would also like to remind you that while we were discussing this, we found out that the behavior of real gases can very well be described with respect to the ideal gas behavior with the definition of residual properties or departure functions. We had discussed how the evolution or the definition of these departure functions. If you recollect, what I had done was I had initially proposed that on a PV plot, I have some particular, or on a PT plot, if you take, it was a TP plot as far as I remember, we have some particular gas at 1 and we need to take it to 2. So therefore, I had proposed which path are we going to adopt. Is it going to be this path or is it going to be this path? And then finally, we found out that it does not matter whichever paths we take, but if we have to consider the availability of data, then we would not accept, or rather we would not like to adopt either path A, B or path C, D. Rather, we would like to go to the low pressure range. We would like to go to the low pressure range, and at this low pressure range, we would like to find out the enthalpy change or the entropy change due to temperature change, and then from here we would like to reach state 2. So this was the path which we had preferred. The only reason being that we knew the Cp, or rather the Cp values are available at low pressure when the gas behaves ideally. And then I had also proposed another path for performing this particular computation, and this path is already provided here. In this path, most of the states that we have intermediate, except the first and the last state, they are fictitious ones. But it hardly matters, because if we start from one state and end in another state, if these two states are the same, then it hardly matters whether we are going from state 1 to state 2 through a fictitious path or through a practical path. It hardly matters. The property changes that we are going to compute will remain the same no matter what path we adopt, if the initial and the final states are the same. Of course, if you ask me what is going to happen regarding the energy interactions, definitely they are going to be different, but at the moment we are just dealing with property estimation. So therefore, the path of execution is not important for us. The initial and final states are important. So instead of adopting this particular path in going from state 1 to state 2, I had proposed an alternative path where we are converting the real gas at T1 P1 to an ideal gas at T1 P1. Then we perform the entire computation that we desire over the ideal gas. We take it from T1 P1 to T2 P2, and after that we convert this ideal gas to the real gas at T2 P2. So therefore, all these intermediate conversions, say from this state to this state and this to this, paths 2 and 3, they are very well known and they are very easily computed. The only hitch for the entire problem was to execute path 1 and to execute path 4. Both of these are fictitious paths. They cannot be performed in practice. What are these? We are converting a real gas to the ideal gas and would like to know the property change for this case. Here we are converting an ideal gas to a real gas. We would like to know the property change for this case. Here we would like to compute the property change at T1 P1. Here we would like to compute the same property change at T2 P2. Right. So therefore, if you observe what are we basically trying to find out in path 1 and path 4, we are trying to describe the property of a real gas with respect to an ideal gas under the same conditions of temperature and pressure. Definitely at high pressure, low temperature conditions, we cannot have an ideal gas state. So therefore, the ideal gas state here and here, they may be fictitious, but it hardly matters, because what we are interested to find out is if the gas could have existed as an ideal gas under any particular temperature and pressure condition, then what would have been the property difference. Now, every time this particular thing, it was motivated from the fact that if this property change can be calculated, then the rest of the computations can be done under the ideal gas conditions, and which simplifies the computations to a large extent. Second thing is, suppose we can define this particular property at any temperature and pressure, we can use this definition and find out this property for other conditions of temperature and pressure. And therefore, we had defined this particular property change here, or this particular change, we had defined this as a departure function or a residual property, and we had denoted it with delta m star, where m is any extensive property. We have already discussed these things. So if m is an extensive property, then delta m star, delta means a difference, m star is the deviation from the ideal gas value. So this is nothing but m minus m0, where m is an extensive property, and suppose this has to be done at some temperature and pressure. So this and this are at the same temperatures and pressures. This we can define for any extensive property. In this particular lecture, we will primarily be confining our attention to the estimation of enthalpy and entropy, keeping in mind that from this we can also compute other properties at our wish. And for this, in this particular lecture, we will primarily be confining our interests to the estimation of delta H star at any Tp and delta S star at any Tp. These are the departure functions for molar enthalpy and molar entropy. This is defined by H at Tp minus H0 at the same Tp. This is defined as S at Tp minus S0 at the same Tp. So once we are in a position to define these properties, then definitely the rest of the computations become quite easy. So naturally, this class will be confined to finding out or to predicting the departure functions primarily of enthalpy and entropy, so that we can use this in order to compute the change of state, or rather to compute the entropy and enthalpy changes when a gas undergoes a change of state from any initial to any final state. Now let us see how we are going to do it. I think I had already discussed some part of it earlier, and I'll just be proceeding and finding out the discussions once I have the expressions for delta H star and delta S star. And before that, I would just like to remind you, this also we had discussed earlier, that this concepts of residual properties or the equations which define residual properties, they just show the true worth of ideal gas equations, and they just show that the ideal gas equation can serve as a convenient base to estimate real gas properties. And it's also important for you to remember that we can have residual properties for gases, for condensed phases as well as for gases, but they are particularly advantageous for gases. Why? Because if you are trying to find out the residual properties of condensed phases with respect to an ideal gas, at the same temperature and pressure, the value of the properties will become very large. So our idea was to find out the properties changes from ideal gas equation and then incorporate small corrections to account for the deviation of the behavior of the substance from ideal gas behavior. Usually any such corrections, they are desirable when the deviations from the ideal gas behavior are small. So naturally, if you are computing these residual properties for condensed phases, the corrections will be very large and it's not very worth in that particular case. They are primarily useful for finding out the property changes in real gases. Along with that, I would also like to remind you that all these residual properties, they arise just because the real properties are functions of pressure, and for most of the cases the ideal properties are not functions of pressure. So therefore, the difference between the real and the ideal gas property, primarily for both the cases, the variation of temperature are more or less the same. It's the variation of pressure which is important, and for condensed phases they hardly vary, the properties hardly vary with pressure. So with everything put together, residual properties or departure functions, you may use any term at your convenience, they are primarily applicable to real gases and real gas mixtures. We will be dealing with property estimation for real gases in this class. Real gas mixtures will be dealt on later on, right? And after this, if you recollect, we had also defined H minus H0. How had we defined H minus H0? We found that in the variation with temperature, that remains the same for both the cases, right? So therefore, the residual property, it is primarily arises because H is a function of P. I believe I had already done the derivation earlier, and therefore we know this expression. This expression is obtained from this particular equation that we had already discussed earlier. So this is the expression for the departure function of for enthalpy, and this is the expression for the departure function for entropy. Once we can find these two, we can use any particular equation, or rather all the other properties can be found out from these two departure functions, and maybe the departure function for volume, etc., which can be easily obtained. We can find out all other non-measurable properties. So therefore, the main challenge of finding out delta H star and delta S star is to compute this particular integral or to compute this particular integral. How to do this? One thing is, we find that this integral, it is a function of, let me see if I can write down this integral. We find that this integral, it is going to be a function of the PVT behavior of gases, isn't it? We can, I'll just write it down for solving it. This is given as integral p equals to 0 to p v minus t del v del t at constant p dp. Or in other words, very sorry, this is delta H star equals to, right? Or in other words, we can also write it down as integral p equals to 0 p v dp minus t integral p equals to 0 to p del v del t at constant p dp. In the same way, we can also write down delta S star as minus integral p equals to 0 to p del v del t at constant p dp minus integral p equals to 0 to p r dp by p and r ln p, right. So therefore, apparently if you look at these expressions, what do you find? If you have the PVT behavior of the gases, it becomes very easy. We have already discussed the PVT behavior of the gases, right. So therefore, from those particular expressions, if you can substitute, rather if you can express V in terms of P, then you should be able to find out this integral, and if you can compute del V del T at constant P, and then you can express it as a function of P, you should be in a position to find out this particular integral. This is quite easy, right. But if you go back and if you observe the cubic equations of state that we have discussed, say for example the van der Waals equation of state, we had, in what way did we express the van der Waals equation of state? The van der Waals equation of state, usually we write it down as RT by V minus B minus A by V square. Same way, we usually for the Peng-Robinson and the Redlich-Kwong equation of state also, if you go back to our discussion, you will find that all these equations are written in terms of P equals to some function of V and T, or in other words, for all these equations we find they are, for these equations temperature and volume are taken as the independent variables, and for all these equations they express P in terms of T and V. So therefore, it is not very straightforward to find out the dependence of V on P from these particular equations. It will be much more useful if we can write down these equations in terms of not dP but dV. Let us see how to do it. It is not very difficult. What do we know? We already know that from these equations, well, I will write down delta H star once more so that it becomes easy for you to follow, and I also have this in front of me, right. Acha. What do we know already? We know that dPV, this can be written down as PdV plus VdP, right. So therefore, instead of VdP, we can write it down as dPV minus PdV. Agreed. Now also we know from the cyclic rule that del V del T at constant P, del T del P at constant V, del P del V at constant T, this is equal to minus 1. Agreed. So therefore, we can express it as del V del T at constant P dP, this is equal to minus del P del T at constant V dV. So therefore, we can substitute this equation, this expression and this expression in the expression of delta H star. What does the expression become? Delta H star, therefore it becomes, instead of V dP, we can write it down as dPV. We will put the limits later on, minus P dV, right. Instead of this, we have these two terms, minus becomes plus in this case, plus T, we have del P del T at constant V dV. So therefore, if you have an equation of this particular form, P equals to so and so, you can very easily find out del P del T at constant V, you can find out P dV, etc., and you can compute this out. Only part remaining are the putting of the limits of the integral. Initial limits were from P equals to 0 at very low pressure to a pressure of interest. Now what is PV at P equals to 0? At P equals to 0, the gas behaves as an ideal gas. So for that case, PV becomes equal to RT. You need to remember that we are all dealing with only molar quantities. So therefore this becomes RT to PV. This becomes at very low volume, it's V infinity to the volume of interest. This is also from very low volume to the volume of interest. So if you solve it, what do you get? It becomes PV minus RT and plus it's going to become plus V equals to V infinity to V T del P del T at constant V minus P dV. Agreed? And this particular term PV minus RT, PV is nothing but equal to, for normal for ordinary gases, this is going to be ZRT minus RT. So this can also be written down as RT into Z minus 1 plus the term which we have written down, isn't it? So therefore from this particular equation we find in a very simple form, once if you know the equation of state, you are in a position to find out delta H star from this equation. So therefore we find that delta H star, it can be expressed as, I just write it down once more for your convenience, integral V equals to V infinity, that's the volume of the ideal gas, to V T del P del T at constant V minus P dV. Similarly, suppose we start working with delta S star at any particular temperature and pressure. It's nothing but equal to S minus S0 at that temperature and pressure. What is the expression that I have already shown the expression here. So therefore using that particular expression, this is minus P equals to 0 to P del V del T at constant P minus R by P dP. We will just replace del V del T just as the way we have done with del P del V. So therefore what does it become? It becomes integral V equals to V infinity to V del P del T at constant V dV plus integral P equals to 0 to P R dP by P. What is R dP by P? Let us see. Again let us find out. We have already said dPV, this is equals to PdV plus VdP, right? Now dPV by PV, this is equal to dV by V plus dP by P, isn't it? We are dividing everything with PV. So therefore from here what do we get? What is dP by P equals to dPV by PV minus dV by V, isn't it? So therefore instead of dP by P, we can substitute it in this particular way, and therefore this becomes del P del T dV from V equals at constant V, definitely V equals to V infinity to V plus R dPV by PV minus R dV by VV integral of this whole thing. So therefore this becomes integral from V infinity to V del P del T at constant V dV plus R, here the integration should range from RT to PV d ln PV minus integral V equals to V infinity to V R dV by V. So from there what do we get? This is basically, this becomes R ln PV by RT plus integral V equals to V infinity to V del P del T at constant V minus R by V whole thing over dV. So therefore, using this equation we can find out delta S star at any temperature pressure conditions. Using this equation we can find out delta H star at any temperature pressure conditions. So therefore, if you know which equation it's going to be valid, you can very well do it and you can find out these two things. For the van der Waals equation of state, as I have shown in this particular presentation, for the van der Waals equation of state, if you calculate, you are going to find out the values as shown. Please do the calculations, they are pretty simple. You just need to evaluate the differentials and perform the integrations correctly. If you do it, you are going to find out that for the van der Waals equation of state, you are going to find out this. Usually we find in hydrocarbon industries, people use the Peng-Robinson equation of state. So if you use the, if you perform the calculations with the Peng-Robinson equation of state, the equation is already provided for you, then in that case you are going to arrive at that or at the expressions which have been provided here. I'll just do it for you in very briefly so that you can just check out whether you have got the same thing or not. Say for any particular property H2 minus H1, this is V1 minus V2 del P del T at constant V minus P dV. I have also already written it down for you, plus delta PV. Right. Now from the Redlich-Kwong equation of state, if you perform these particular integrations, you find this is equal to 1.5 a by t to the power 0.5 integral V1 to V2 dV by V into V plus V plus delta PV. Okay. If you integrate it correctly, this equation, then you find this gives you as 1.5 a by b t to the power 0.5 ln V2 by V2 plus b plus ln V1 plus b by V1 plus delta PV. Now suppose the state 2 is the state of interest and state 1 is the ideal gas state. So therefore, in the ideal gas state, we know V1 tends to 0, ln V1 plus b by V1, this is naturally being equal to 0. So with this we find out H minus H0 by RT, this is given as the expression which I have already written down, 1.5 a by b RT to the power 1.5 ln V by V plus b plus z minus 1. And if you make certain substitutions, then more or less I think, yeah, this is the equation that you are going to get. In a similar form, if you proceed with the calculations of delta S star, then also you are going to find out that S2 minus S1, this is S2 minus S1, this is nothing but R integral V1 to V2 dV by V minus B plus 0.5 a by t to the power 1.5 integral V1 to V2 dV by V plus B. If you integrate it and then you find S2 minus S1 is R ln V2 by B. I am calculating this out because this is quite commonly used in hydrocarbon industries, and since this is slightly involved, so therefore this is t to the power 1.5 ln V2 into V1 plus B by V1 into V2 plus B. Right. If you rearrange it, then we find that once you rearrange it and to arrange it properly, then finally you get S minus S0. This will be equal to ln V minus B by RT minus 0.5 a by B RT to the power 1.5 ln V plus B by V. Right. So therefore, in this particular way, you can also try out the Redlich-Kwong equation of state. We find that from these equations, from the PVT behavior of the gases, if you know that they are obeying any particular equation of state, all the equations are pressure explicit. So using these, you will be in a position to find this out. What are the other ways of estimating enthalpy, entropy, departure functions or other departure functions, because these equations that we have derived, they are although very accurate and exact, but they are very tedious and time consuming. As engineers, we would like to have certain faster methods which may not be so accurate, but they would help us to obtain a quick estimation of the properties. So we are going to discuss that in the next class.